first, we are going to start with a brief introduction about what are we going to talk about today. First, our sponsor and current employer, SoftServe, is a company focused around different parts of the technological stack in 21st century. And we are going to we are part of the cloud and DevOps group. We are providing consultation services for various enterprises that are currently undergoing migration to the cloud or optimizing their current cloud infrastructure or applications. And the purpose of our presentation today will be to describe you how we helped a particular client of our employer. This is going to be a case study, and it's going to follow the path from the beginning of the transition, where this project was assigned to our employer, to where we were a few months ago. And then, of course, there will be a second phase where we are going to describe the current state of the infrastructure. Hopefully, this is going to be a very interesting journey for all of you. A few words for ourselves. Venti, if you can please introduce yourself.
Yep, my name is Ventsislav Kaynakchiev. Venti, short. I have more than 20 years of IT experience. I started as a software developer with PHP and Perl. Naturally switched to Unix and Linux based work, where I, for a while, was a systems administrator. Then I became a DevOps engineer, and my current role is a DevOps architect at SoftServe. I graduated from physics a long time ago, and my relevant certifications for the purpose of this discussion is Google Professional Cloud Architect and AWS Solutions Architect professional level. Okay.
Thank you. I'm a senior DevOps engineer with SoftServe currently. I'm in the IT business for roughly 10 years, and I transitioned there from totally different profession. I was doing various economics and business related activities before that. I switched to IT roughly around 2010 and got another MD in the area. During the years, I'm mostly dealing with infrastructure. Back in the days of the system administration, for some time I was doing some project management, and the natural transition was to become a DevOps practitioner and respectively an engineer. I'm mostly interested in different cloud-based technologies. So I try to focus my skills and attentions on what is the current offering by the three biggest enterprises in the business: AWS, Google Cloud, and Azure. And that's it for me. Now let's talk about the actual case study. First, we're going to describe to you what we understand under the term of immutable infrastructure, and why have we chosen to start our journey there. We're going to review how the infrastructure looked like before we intervened. We're going to describe our planning work. We're going to describe our actual implementation of our plan. And we're going to analyze the state of the infrastructure after finishing phase one. So there will be something like a before and after comparison. And we're going to respectively describe why we need to undergo phase two in this transition. So when it comes to immutable infrastructure, I want you to compare basically having a pet and having a cattle. I hope that nobody is going to get offended by these terms, but with immutable infrastructure, we actually don't care about our servers in terms of that whenever a server starts misbehaving, it's usually easier to destroy it and reprovision anew rather than try to fix it, which was the old school way of doing system administration. And our journey is to make sure that our client does not have any stateful servers which need to be taken care of by system administrators. Every change or any issue with a server means basically redeploying of the whole server. And now, Venti, if you can go over the legacy infrastructure briefly.
Well, our company was approached by this prospective customer who is a company working, implementing machine learning and big data analysis applications for fintech and other major enterprises. They have a number of proprietary Java microservices. They use Hadoop cluster, which basically performs the heavy processing. And they use Elasticsearch for long-term data storage, access, and classification of data. And in addition to that, they have a MySQL database to keep some of the application states, logs, etc. Probably I can provide some background here. When we were approached, they told us, well, we have this configuration management tool developed in-house, but it takes about 2 months to prepare the infrastructure for a single new customer, because they need to set up a number of infrastructure resources, like all of these instances, data storage, etc. They need to set up everything in order to deploy the applications correctly, and then they need to perform days or weeks worth of testing in order to ensure that everything works well. Okay, please, if you would describe the infrastructure at a high level.
Sure. So we have outlined the very high-level infrastructure layout in this diagram here. It's not descriptive by any means. We unfortunately don't have the option to go into much detail because most of the low-level technicalities are really proprietary to our client, and we are having a non-disclosure agreement with them. But logically, the application itself is layered into 3 layers: a front end, a middle tier, and a back end. And in here is the proprietary front end. This is a series of microservices that accept different types of connections. Some they're responsible for ingesting big volumes of data. Some they're responsible for providing RESTful API interface, and some have a management website or place to upload large files. This does not mean single server. This actually means an array of servers, and it's a cluster on its own. So this is why I'm saying it's very high level. As visualization tools, they're using several open source solutions like Tableau, Kibana, and Airflow for managing the actual workflow. The middle tier and the heavy duty data streamlining is done in a Hadoop cluster. There is also some decisioning happening on Elasticsearch level. This is why we have put Elasticsearch both here and in the backend, because there are some pieces of Elasticsearch, the data cluster, which are consistent as stateful data storage. Of course, there is also an underlying database, and all the objects that can be safely stored in a cloud bucket are stored in such. The communication between all the components is secured by Kerberos authentication, and this whole thing is orchestrated by a configuration management solution. When we started working on this project, they were using the Salt stack here. And
Well, just to add something here, they used their own solution based on SaltStack. So it was very proprietary.
yes, nice addition. Thank you, Venti. Um, and all this was hosted on Google platform, but basically you can just cross out Google Cloud from here and you can host this same stack on AWS, on Azure, or even in your, let's say, VMware-based private cloud. Nothing really changes. So the biggest issue here is that practically the customer was not using any of the good stuff that the modern cloud provider offers. Any of their services can be hosted on virtual machines, which can be even hosted on your personal laptop if you feel like it. So this means that the client was not using most of the benefits that come out from being a cloud customer. And we're going to go into a bit more detail here in the issues and see if you can go over them.
Yep. So some of the issues, well, their major issues were that they lacked any meaningful automation at the cloud provider level. They had a number of security issues they had to deal with because it was very hard to apply any sort of configuration fixes once a server is deployed. They had no auto scaling. All scaling up and down was done manually. They had very complex security requirements with regard to their particular customer. They are defined based on customer needs and on customer questionnaires. So each new project had a different set of configurations. And all of this logically led to very high cost overhead because basically all of the instances were single process. They had a single role, and logically they were over provisioned. So we had, let's say, 30 or 40 different instances. Each one of them hosts a single application, and it's sized, let's say, twice or in some cases 3 times the requirements of this application. And there were most of these hosts were up and they were not turned off outside of business hours. That means that this cost aggregated to very, very significant numbers.
Okay, so to wrap it up, this practically means that the client has to a great extent lifted and shifted their application from an on-premise infrastructure to a cloud environment, which is, as most of you already know, this is the first step to a cloud migration, but it's definitely not the final and shouldn't be considered final, because if this is the only action that is taken for the migration, this usually means that the client ends up paying more without any added value for their additional expenses. And this is where our role as consultants come in to plan how to make sure that we have infrastructure that is provisioned faster, it's provisioned in more secure manner, and it's provisioned in easily replicable manner. Because if we go back to the diagram, this means only one environment. Every client of our client has such an environment, which means that these pieces of infrastructure need to be replicated 5, 10, 50, or 100 times. And if you do this manually, this means that you'll be doing lots of errors, even if there is some sort of a configuration management based on server image. So let's go to our plan. This is what we offered to our client, and this is what we worked on several months to get this put in place. The first problem with migrating to a cloud is you need to know where and how are you going to store your stateful data. And for this, you need to draw the line between the services which are considered stateful and ones that are not. This is going to define their infrastructure requirements. Respectively, when you outline the stateful services, we need to find a way to division the stateful part from the actual application and turn the application into another stateless service. Since the client uses different open source solutions, which are atomic in nature and cannot be easily decoupled, the stateful from the stateless part, it's not a very easy task, and I cannot say that it's done with 100% success, but at least some steps are done. So some steps are taken in this direction. The next step is to build an automated environment build-out tool that automates the provisioning of all the cloud-provided resources. In this case, this is the network, the identity and access management rules, and the secret storage. One of the other requirements from the client was to implement zero trust. There is a typo in the presentation, sorry about it. We're talking about zero trust access security tool, which will allow clients to access the applications on a need-to basis via automated interface. We are going to talk about it in a bit. And respectively, as DevOps engineers, we were tasked to build a continuous integration pipeline, which utilizes best infrastructure as a code practices to promote changes to the environment during predefined maintenance schedule, which means that we are considering one environment to be a piece that can be easily destroyed and reprovisioned in a single click of a button when and where it's needed, given for an upgrade, for a cancellation, for provisioning of a new client, or any of those use cases. And here, Venti, you can go over the steps for this.
So here is what we did as part of this transition. We built a number of Terraform modules to cover all the basic cloud resources, the VPC, the networking, the IAM roles, as well as additional cloud storage buckets, etc. There are a number of different underlying resources. Then we built a Packer pipeline to build role-specific images. So basically, for each type of server, depending on what application set needs to be installed, we have a baseline image on top of which we deploy a number of software artifacts from a private repository. And this image then is used for the deployment of the service. We set up a proper naming convention for different systems and environments, which helped us easily parameterize all the environment-specific configurations, so that we can start with the same template and only apply specific changes where they are needed. And then we have a number of Terraform modules to actually provision servers from the pre-built images and populate their configurations based on the parameterized templates. All of this is supposed to provision an environment based only on the code we have in our Git repos, and no additional customer input or operator input. Okay, do you have anything to add here?
Sure. There are a few more steps here that were taken. There was a need to build Terraform modules to maintain the state of the current storage solutions. The storage solutions at the point of finishing the phase 1 were limited to Google Cloud buckets and Cloud SQL databases. The state is maintained by means of ensuring that the databases do not grow too much, to one extent, and to other that the buckets again do not grow indefinitely. Some of the buckets were used for long-term storage of enormous amounts of data, which is really important to make sure that a proper life cycle is in place, and data can be archived and respectively deleted after a certain period of time has passed according to PCI regulations, etc. Additionally, we needed to, after all, build some sort of a configuration management tool that takes care of post-deployment tasks. Even that initially the plan was to get rid of such requirements, the specifics of some of the software pieces required it. We ended up choosing Ansible because it's very easy to be turned into a masterless configuration management tool. One of the pain points with the old proprietary salt stack based solution was that it's required to have a living server, a master, which was considered sort of an attack vector against the infrastructure. So the configuration management tool that we were going to implement was going to, one of the requirements was to make sure that it's masterless. Also, we needed to build some automation around the zero trust access tool. It's Prevex. This is a tool offered by SSH.com as proprietary version of, I'm not sure if you're familiar with tools like Okta. Prevex is a competitor to those type of tools. They provide single sign-on integration with various directories for users and backend integration with various services via different protocols like SSH, web HTTP, and even RDP if there is a Windows environment around it. And of course, we need to make sure that Prevex is properly utilized without any manual intervention in there. So a new environment after build out should have all the rules associated with making sure employee X can access server Y whenever he needs to and not out of this window. So all those rules are part of some, let's say, quite complex automation and scripting again. And eventually, all those different pieces that we described above are wrapped up into Jenkins pipelines, which can be used either as manually executed or scheduled to be run at a particular time window or a particular schedule. So these are the steps taken to implement phase 1. And here is how the infrastructure looks like after implementation. Venti, if you can go over it.
Yeah, well, most of the components here are still the same, but the main differences here are that we use Terraform for all the cloud resource provisioning. This means that we have a number of states for each one of the layers we deploy on. So let's say we have a Jenkins pipeline, which deploys layer 1, which is the basic cloud project setup with the VPC, the networking, the IAM roles, which need to be available as dependency for all the next layers. Then we have another layer which deploys the backend tier. These are the Cloud SQL instances, the storage buckets, the Elasticsearch backend, and middle tier cluster, because it's a single cluster, even if it has several different roles at different tiers. We use Google Secret Manager to store our secrets. And of course, all of the Terraform states are stored remotely in cloud storage, so that on one hand they are archived and we can return to previous versions if something happens with the current state file. On another hand, we ensure that while this cloud storage is intact, we have a state which ensures that these resources are set up in exactly the way we expect them to be. Another layer is the Zero Trust Access solution with PrivX. So there is a set of 1 or 2 instances, depending on the environment, which are specific to this project and which connect to the central PrivX infrastructure we have as a separate project. And we have the Kerberos authentication, which is used by all the application services on higher layers. And then we get to the application layers, which are the proprietary services and the additional tools which are used for data analysis and visualization. Together with the services, we also deploy a number of load balancers, which are not shown here. Oh, we have actually a line with the load balancers. We have a number of firewall rules, which are deployed as part of the basic networking infrastructure. And we provision a number of Google managed SSL certificates for the HTTPS access. What am I missing here? Well, the Ansible, well, we say it's masterless. It's not exactly one. It's just that it doesn't have a permanent, a persistent instance, which we call Ansible master. The way we set it up is that each instance, when it starts, needs, well, not all of them, but most of them need some additional configurations, which might be which cannot be efficiently managed in a fully static manner or templatized manner, which often change with time, etc. And we also have a number of tests, of automated tests, which are put into Ansible. So for each server role, we have a separate Ansible role, which we run on this server, and we know that it has all the expected configuration objects, all the services we expect on this node are actually up and running and responding. And for example, that an application service can access the Elasticsearch, the Cloud SQL, the Hadoop cluster, etc. All of this is automated using Ansible. Ogi, anything else on your side?
Yes, I want just to add here that not sure if it's very visible from the diagram, but indeed this is I think PCI related, PCI regulated environment, which means that it supports full end-to-end encryption on every single component, meaning that no API call can go on any non-HTTPS route. And Google covers this by offering managed layer 7 load balancer on the front end. However, all the interaction between components between the front end and middle tier and the back end as well is covered by the self-signed certificates orchestrated by a tool known as Small Step. It is used as a certificate authority for closed internal environment, and it turned out to be very flexible and useful for our specific use case. It means that we can basically rotate certificates every hour if needed. We're not doing it, but if necessary and if there is a requirement to do so, we can rotate certificates every hour to make sure that there will be maximum security and nobody can really do any sort of man-in-the-middle attacks on any of the stacks. And the small step server, which orchestrates the certificate provisioning, is again hosted on the Kerberos layer. And this is one additional security step that's being implemented, and it's currently, I would say, state of the art in terms of security and encryption of traffic in motion. Other than that, yes, basically we have taken all the tools that were in there before and made sure that they can be seamlessly replicated if needed n number of times as time passes. This was the idea of phase one. Of course, afterwards, after phase one was finished, there were multiple pain points which still need to be addressed. And they basically require us planning phase two. We're not going to talk about this today, but the pain points on a very high level are the fact that maintaining immutable servers with SSH access to them actually technically allow for manual changes to be done. And it's really rare and it's really considered ad hoc exception, but it's not impossible, which means that while we still support fully blown VMs as infrastructure, we cannot be really immutable. Of course, there is also a cost overhead of deploying and utilizing those VMs, even though they can be started and stopped when a given service is started or stopped. For instance, as you might imagine in this diagram, the Hadoop cluster is very heavy in terms of compute requirements. It consists of about 10 servers with maybe up to sometimes up to half a terabyte worth of RAM. If you have this thing available 24/7, it's going to cost a fortune. So
just a note here: the cluster, the Hadoop cluster itself, costs more than half, probably close to 2/3 of the overall infrastructure.
Yep, very good call. So even though we have gotten to the point in which all the services are basically started only when they're needed, which means that Hadoop is started only when a job is processed, which happens on a regular interval, like twice a day or something like this. Even though starting a server adds some overhead to the cost, because first you need to support the underlying operating system, and second, there is the boot time you need to take into consideration, and the inevitable startup bootstrapping that happens on every boot. Um, it takes between, let's say, 2 and sometimes 15 minutes on some of the more complicated setups, which is overhead, which shouldn't really be happening. And the other pain point that we need to mention here is that we have gotten to the point in which the CI pipeline is in place, but we are not yet in a position to do a full continuous deployment. This is to some extent due to the client not allowing it, and to some extent that actually having continuous deployment hosted on static servers is not always ideal and can lead to a wide array of problems. We need to know that even though cloud providers offer very reliable boot mechanisms on their virtual machines, there is always a chance that a given server might simply not start when it's supposed to. And we have seen this many times, especially when we shut down and start some servers up to 10 times per day.
Yeah,
There is
I would like to expand on that if you're
Sure.
finished. Yeah. So it's mostly a matter of culture and business requirements. Since we are dealing with large enterprises, with banks and other large organizations, they do not feel well about performing constant updates in these environments. So we tell them, well, we can push updates several times per day if needed, with minimal or no loss of availability. But they prefer to have these updates, for example, on monthly basis. We had to fault with the customers to allow us to update on bi-weekly and in some cases on weekly basis, but not in production yet. So we are still struggling to demonstrate that if we are able to perform smaller changes more often, this would lead to fewer errors and fewer and shorter downtimes than if we need to keep all of the updates for a single large monthly update. Sometimes even it's not monthly, but they insist on having it once per 2 or 3 months. And from security perspective, this is another big risk because since we are dealing with immutable servers, we do not perform any regular lifecycle activities like updating packages or changing some configurations, some system level configurations in place. Whenever we need to perform any serious changes on these servers, we basically recreate them. This leads to some short downtimes for some of the services, not for all of them. And in general, the customer should not be affected, but still, this is mostly not on us, but on the business side to decide whether they want this or not. Technically, we are prepared to do it. Sorry, I interrupted you.
That was actually a great addition. The truth is that heavily regulated business, which is fintech, is somewhat drags behind in current popular threats for various reasons, because it's usually very hard to promote new ideas and frequent updates in that area. But that is changing. with some organizations, so it's a matter of time before it's adopted to pretty much all around the world, which is a good thing. Now, given all those pain points in mind, the essence of phase 2 will be a migration to container-based workloads. It's a very vast topic, and at the given point of time, we have pretty much completed it, and we can speak about this activity in our next session when our hosts allow it. Hopefully, all of you will be available to join our next presentation. Please check with organizer about the exact date, but in our phase 2, we're going to speak about migrating all these workloads to containers, as well as some serverless technologies offered by the cloud provider. And with it, we aim to basically mitigate those last 3 painful items that remain, and which basically differentiate this client's infrastructure from the current state-of-the-art trends in DevOps world. Venti, would you like to add something here?
Well, we don't want to spoil the next lecture, but basically we use GKE clusters, which is the Google's Kubernetes engine managed service. In order to actually do that, we had to set up a hybrid infrastructure. So instead of replacing everything we had by now with the Kubernetes infrastructure, we set it up in a separate network, so in parallel, and enable only the services which actually need to be accessible from one or the other side to the legacy, or in the other way. So from that perspective, it's more like a continuation, not a replacement. Hopefully, one day we will be able to destroy all the legacy infrastructure resources and keep only the Kubernetes and serverless and managed Google service resources. But we are not there yet. The good part is that with this shift towards container-based workloads, the customer actually changes their view on how these services are deployed, how they are managed, how they're maintained. By the way, we didn't mention monitoring here or any security tools, but we have them. All these integrations are fully automated in the current infrastructure, and we are working on automating these services with the Kubernetes infrastructure and the respective applications which are actually deployed in Kubernetes. Ogi, if you have anything else to add here, I think we have a question we can answer too.
Yes, I'll be stopping my screen sharing, and I'm going to give the word back to our host, Kasia.
Yes, guys, thank you so much.
For the QA session, guys. If there are any questions in Polish, we'll need a translation, but we'll try to answer everything.
Yeah, of course. There is one question from Paweł Ufnalewski. Please read it and answer the question.
Yeah. Does Privex allow you to record SSH sessions? That was actually one of the requirements. We evaluated several different access tools, access solutions. So on one hand, these tools are used as a single source, as a single place from which this infrastructure can be accessed. On another hand, all of the users which need access to these environments, they need to have specific roles to specific environments, and all of these sessions need to be auditable. So with that perspective, Privex gave us all of these and more. And yes, one of the things Privex does is to record SSH sessions. I would say that it's not ideal with that regard because it doesn't store them as text records, which are searchable, but it treats every session as a remote desktop session. So whether you access these servers via SSH or you access some web services, or probably you have a remote desktop protocol solution, be it on Linux or on Windows. All of these are treated as remote desktop sessions, and they're recorded as video. But we have implemented a number of additional reporting tools on top of what Privex provides. The one great thing Privex has, which we couldn't find with any similar solution, was that basically anything it does is managed via its API. So we were able to set up API calls to have full integration, full automation for all the life cycle for the whole life cycle of the environment. So we automatically provision all the host and gateway definitions in the central Privex server, or we are able to deregister them when they're destroyed. We are able to update the service definitions for each host. So each host has by default an SSH service. It has a number of web services if it exposes any, and it might have an RDP service as well. We actually have an RDP server on Linux. Currently, we don't deploy any Windows machines on these environments, but we could, and then we would have RDP exposed as well for these Windows machines. And then we actually use the reporting, the APIs to pull all of the auditable events, so we can easily match an event when a specific user used a specific role to access a particular host in the environment the user has been given access to. And once we know that this event matches some unexpected change or something we need to investigate further, we can actually find this exact recording for this particular session and review it if needed. I hope that answers your question.